Hello, AP Chem students, and welcome to topic 6.4, heat capacity and calorimetry. The learning objective for today is 6.4.a, calculate the heat Q absorbed or released by a system undergoing heating or cooling based on the amount of the substance, the heat capacity, and the change in temperature. There's quite a lot of information in this section. Also, this is directly related to a lab. If you do not get a chance to do this lab in class, I would highly recommend that you go watch a lab video on YouTube and or do a lab simulation online, because this is a lab that shows up pretty frequently on the exam. It's a classic. So here we go. So remember the first law of thermodynamics, which states that energy is conserved in chemical and physical processes. This means that although energy can change form and transfer from system to surroundings, it can always be accounted for. So chemical systems can change their energy through three main processes. Number one, heating and cooling. Number two, phase changes. And number three, chemical reactions. So you may remember this when we did LOL diagrams last year. Those of you that took chemistry with me, they looked like this. And other chemistry teachers use these as well. So you talk about the thermal energy, the phase energy, and the chemical energy, and how that can change as you go through a process. So there are types of systems that we think about when we're studying energy. So both the matter and the energy involved need to be accounted for. So there's three types of systems that we're going to think about when we're setting up our energy studies. So the first one is called an open system. And when you have an open system, that means that heat can transfer in and out of the system. Mass can also transfer in and out of the system. So for example, if this is a liquid and it vaporizes, you're losing mass from the system to the surroundings. That's an open system. So that would be something like a mug of coffee sitting on the table. Then you can have a closed system. And in a closed system, you're not going to have a transfer of mass, but you can still have a transfer of heat. So that might be something like making sun tea, for example. If you set a jar on a counter and you put a tea bag in it and you let the light have access to it by having it in a clear jar on that windowsill, you will eventually have some tea that's brewed. Then you have an isolated system. In an isolated system, you do not have heat transfer with the surroundings, nor do you have mass transfer with the surroundings. And so that would look like something like a sealed thermos. Now, is this a completely isolated system? No, eventually that coffee will get cold. But if you've ever used a thermos that's really good, it actually can stay hot for quite a while. So that's our assumption that that's an isolated system. In calorimetry, we assume that we're going to create an isolated system. Again, is it perfect? It is not, but we're going to do our best to do that. And by creating an isolated system, then we know that both mass and energy are conserved. And so we can account for the energy changes that are happening in our reaction setup. So calorimetry is the process of measuring quantities of heat. So here you've got your setup. Usually it's done in an insulated system that we assume to be isolated, like we talked about. And this allows us to perform simple calculations based on the law of conservation of energy. So we assume that if your system is dissolved in the water or is sitting in the water, you can have both of those things happening. All of the energy that is lost or gained will be exchanged with the water itself. So we're assuming we're not losing anything through the walls of the coffee cup. And we also often put a lid on top, and then that also keeps us, we assume, from losing energy. Now, there's an extremely precise version of this technique called bomb calorimetry. And those of you that might go into chemistry studies in college will probably do a bomb calorimetry experiment when you get to physical chemistry. Bomb calorimetry is very well insulated, and therefore it is very, very close to an isolated system. And so you can get very precise energy measurements in that way. So in this case, heat is lost or gained by the system and then transferred to the water, which is considered to be the surroundings. So the calorimetry labs, a simple lab can be done in 2 nested coffee cups with a cardboard lid. These readily available materials are actually surprisingly good insulators. The system being studied is placed in the inner cup, and the premise of calorimetry itself is pretty simple, and it helps to keep in mind these straightforward facts. Okay, first of all, heating a system increases the energy of your system, so remember that. Cooling a system decreases the energy of the system. And then finally, in calorimetry, again, the same idea that all energy is lost by the system is gained by the water, and vice versa. So you have this exchange going on inside your cup. So this brings us to the idea of heat capacity and some calculations. When you're examining 2 different types of matter, the transfer of the same amount of thermal energy will not cause the same temperature change even in objects with identical masses. And that's because of a difference in heat capacity. So heat capacity is the amount of heat required to raise the temperature of a system by 1 degree Celsius. So if you look at this graphic here, copper has a specific heat of 390 joules per kilogram degree Celsius. Aluminum is 910 and water is 4,200. So what a lower specific heat capacity means is it warms up and it cools down quickly, and it takes less energy to change its temperature. Versus water has a higher specific heat capacity. It warms up and cools down more slowly, and it takes much more energy to change its temperature. Now, the other thing I want you to know about heat capacity is it is impacted by state. So steam, gaseous water, has a different heat capacity than liquid water. So heat capacity is an extensive property, meaning it depends on amount. So to avoid that fact and having to measure it every single time, we use molar heat capacity or specific heat. Specific heat is an intensive property that actually can be used to identify substances, and that is a classic copycat calorimetry lab to do, to identify an unknown metal by calculating its heat capacity, specific heat. So molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin. Specific heat capacity is the heat required to raise the temperature of 1 gram of a substance by 1 Kelvin. It's abbreviated with a lowercase c. So you just have to kind of pay attention to the information that's given to you to figure out if it's molar heat capacity or specific heat capacity. We usually see specific heat capacity. The units of specific heat capacity are joules per gram degree Kelvin, or sorry, no, we do not use degrees with Kelvin. Joules per gram Kelvin, or joules per gram degree Celsius. There we go. Okay, so specific heat capacity, continuing this conversation. When you're doing calorimetry, calculations at constant pressure, my timing was strange there, but we do these calculations at constant pressure, which we assume is atmospheric pressure in our labs. We use this equation. Q is equal to MCAT. So in this case, Q is equal to your heat, M is mass of the system, C is specific heat, and delta T is the change in temperature. So you can see 1 gram of material has different impacts on temperature based on the specific heat. Okay, so remember to watch your signs, and usually with calorimetry, you need to assign your signs, you need to think about them. So whatever substance is losing the heat will be negative, and whatever is gaining the heat will be positive. So while it's not a part of the SI system, a unit you often hear in your life is calories, which is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. And so therefore, 1 calorie is 4.184 joules. Okay. So if you are asked, and I mentioned this a minute ago, to determine an unknown specific heat, you can apply the first law of thermodynamics to figure it out. So you do this by finding the specific heat of the unknown in a calorimetry setup. So you would set up a Q situation where you have MCAT equals MCAT, because we assume that all of the heat that is lost by the unknown, and let's just talk about an unknown metal for simplicity. So any heat that's lost by the metal will be gained by the water. So what you do is you heat up the metal so that it's hotter than the water, and you put it down in the water, and you measure the temperature of the water before you begin, and then you watch the temperature change of the water over time. And so eventually the metal and the water will reach the same temperature, and then you can do your calculations. So if you look at this setup, if we apply the direction of the energy flow based on the situation, we would know that the hot metal would have a negative sign because it's losing heat, and the water would have a positive sign because it's gaining heat. So you can see that here. I put hot as red over there, it's losing heat, and cold as blue, it will gain heat. Now, when you talk about a special case, which is the case of dissolving a solid. So in the case of dissolving a solid, the direction of energy flow is determined by remembering that water is considered to be part of the surroundings. So if the temperature of the mixture increases, then the dissolution is exothermic. If the temperature of the mixture decreases, then the thermal energy was absorbed by the dissolution, making it endothermic. Okay. Also, when we're thinking about the solution and doing Q equals MCAT, you do need to sum the masses of your solid that you are adding and the water. because you end up with the solution overall, and so you do need to sum those masses. Usually when you're forming solutions, you are told to assume that the specific heat is the same as that of water, because the water will overwhelm the system because it's in much greater excess, and then you can calculate a Q value for the amount of heat that is released by the dissolution of that solid. Okay, so what should I be able to do with this? You should be able to calculate any variable contained within the equation Q equals MCAT for these processes: heating and cooling, phase changes, chemical reactions. You remember that with phase changes, we talked about how you actually would use a different quantity for this, which we will get to. You have like your delta H fusion and your delta H vaporization. I believe that's coming up soon. But I was going to go somewhere else with this, and I totally lost my train of thought, so we'll just go on. Use conservation of energy to calculate change in the temperature of a substance based on the heat lost or gained by another substance in the system. And I believe that is it. So I will see you soon for our next topic in thermochemistry.